And here we are for lesson 5.2.4. Enjoy the ride. Lesson essential question: does it matter if the value of the function equals the value of a limit? That's what we're going to look at, and we're starting with problem 5-80. And during the course of this lesson, we're also going to more clearly define what continuity is for a graph of a continuous function. Part A, given the function g of x sketched at the right, does the limit as x approaches 3 of g of x exist? If so, evaluate that limit. So if we're approaching the x value of 3, that would be this vertical plane here, where x is 3. If we're approaching it, tracing our fingers from the left, tracing our fingers from the right, will our fingers meet is the question. The answer would be yes, they would. And then where do they meet? And again, we're looking for a y value there. Y would equal 2. So the limit of g of x as x approaches 3 is 2. And again, do our fingers coming from the left and coming from the right, do our fingers meet? Given the function h of x sketched below, evaluate the limit as x approaches 3. So here we go again. Graph looks similar. The graph looks similar as the last one, except now we have this sort of point, random point, floating above the graph. Does that affect the limit? As we're approaching from the left, I believe Hank asked this question today in class, and we're approaching from the right, where will our fingers meet? Again, in this particular case, our fingers will meet at 2. So the answer does not change for the limit statement. Part C, evaluate h of 3. That's where this missing point, or this random point, comes into play. Because if we do go over to the x value of 3, what is the y value that corresponds? It's not this point, because that's an open circle. It's this point. Equals 3. Does the value of f of a affect the limit? No, it does not. They can be two totally different answers. Moving on to problem 5-81, we give our formal definition of continuity. There's 3 parts to this checklist. If any of the 3 are violated, then the graph is not continuous. All 3 must be true in order to call a graph or a function continuous at a particular point. First of all, that point must exist. The limit at that point must exist. Finally, the limit and the value must be equal in order for the function to be continuous. That's the checklist we're going to use. In a problem like 5-81, if f of x, part A, f of x equals 1 over x plus 3, is it continuous at -3? Well, first idea would be to sketch that graph. So left 3 gives me my VA. My HA is at 0 because there's no vertical shift. I'm sketching the graph. It's a hyperbola. And then I ask myself a series of questions. First, does f of -3 exist? Is the first stipulation. So I go to the value x -3. Is there a point there? No, there's a VA. No, not continuous. Do I even need to move on to evaluate the limits? And the answer would be no. Continuous. Continuous. Sorry, I can't spell. Moving on to letter B. In letter B, we have an exponential graph from Algebra 2. Exponentials have an HA, no VA. And that curve should look something like this. Again, that's a sketch. And what we're looking at here is the x value of 0. So at the x value of 0, will the graph be continuous? So, stipulation number 1, does f of 0 exist? Answer yes. F of 0 equals 1. 1 is the y value at that point. 2, does the limit of f of x as x approaches that value 0 exist? So if it's a limit, that means we're approaching it from the left, tracing with our finger, from the right, tracing with our finger. Will our fingers meet? If our fingers from the right, from the left, will they meet? Yes, they meet. Where do they meet? They meet at 1. Finally, does the value from part 1, f of 0, equal the limit from part 2 as x approaches 0? The answer there will be yes. Therefore, this graph is continuous at x equals 0. Part 3, we're going to look at a piecewise function. And in that piecewise function, the first part of it is a linear curve. It's 2x plus 3. So that's a starting value of 3. Okay, and all values less than or equal to 2. So if I plug 2 in there, that's 4, that's 7. Okay, and it's going to be somewhere around here. That's a closed-in circle because it is an equal to symbol. And then that's for all the values less than 2. So let's see, down 2 over 1, down 2 over 1, something like that. That's what the graph looks like for the linear portion. For the parabola portion, I have x squared plus 2, 2 squared is 4, 4 plus 2 is 6. So that's going to be an open circle, and then it's a parabola shape from there. Which kind of goes off my grid there, but that's okay. Now, again, I'm going through my checklist. Does the point f of 2 exist? So I go over to the x value of 2. Do I have a coordinate there? Oh, not there, that's a hole. But there I do. What is the coordinate? It equals 7. Check 2. Does the limit of f of x as x approaches 2 exist? So now I'm tracing with my fingers, tracing from the left, tracing from the right. Will my fingers meet? Right finger's going there, left finger's going there. Will my fingers meet? No. The limit does not exist. Do I even need to do step 3? No. Not continuous. So again, if any of the 3 are violated, we don't need to finish. We can at that point say that it is not continuous. Last, we have the graph of x squared minus 16 divided by x minus 4. You might look at that. You might look at that and say that that's one that we're not really comfortable with off the top of our head. So we're going to take out our calculators and we're going to graph x squared minus 16 divided by x minus 4. As soon as we get loaded up here. There we go. Turn that on. Y equals, we're going to go x squared, parentheses first, x squared minus 16